My project is on smoothness-constrained phase decomposition for vibration sensing. So the kind of vibration that I'm looking to measure is those subtle vibrations in a scene that is really hard to capture with your with your bare eyes. An example of this would be when the string on the guitar makes a sound, it would likely vibrate, but this vibration cannot really be picked up by human eye. So the left video would be what you see, and the right video is a motion magnified version of this video. So as you can see, the second string is constantly moving up and down at a certain frequency and amplitude. And this is the kind of result that I'm trying to achieve with my project here. So the way that I'm trying to do this is with electronic speckle pattern interferometry, which basically on a higher level is the system where there's a camera, a laser, and a beam splitter that splits this laser beam into two. Oh, so we now arrive at two separate beams, but they're all coherent with each other. So when these two separate beams recombine on the object surface, they would create an interference pattern known as speckles. And these speckles are really sensitive to any motion or deformation on the object surface. So once there is some change on the surface, that means there would also be some path difference that would change across the two beams, which can lead to a constructive or destructive interference. And this interference is what we use to look for the phase difference from deformation. Thus, we can frame the intensity image as an equation of A plus B cosine theta plus delta, where A, B, and theta terms we can assume are related to the scene, but would stay constant under any deformation, where A is the background, B is interference amplitude, and theta is the phase difference. And what we actually are looking for is the phase difference from deformation, which is the delta. Since we only know I to decompose for U and V, we can kind of put this in the framework of two separate matrices. Um, by decomposing into U, the left matrix, which contains A, B, and theta values, which are invariant across time, and the V matrix on the right, which consists of delta, which we assume is invariant across space. That gives us a nice matrix multiplication from n times 3 and 3 times m, resulting in like a intensity image of dimensions space times time. However, this invariance across space is not necessarily true. In fact, delta may vary smoothly across both space and time. So now, because of this, we want to apply the Horn-Schunck algorithm, which better captures this property. Horn-Schunck algorithm framework is something typically used for optical flow, where you see here this term U and V are the horizontal and vertical flow of the image. So this brightness constancy term that has IU plus IYV plus IT minimized to zero is looking really similar for the as the expanded equation of I, which is B cosine theta cosine delta plus B sine theta sine delta plus A minus I, where B cosine theta, B sine theta, and A minus R are basically the IX, IY, and IT term that we give us as input if we know what U is. And to get U, we can use like some initialization calibration on like I equals UVT. That's another project. And then for the smoothness term, we can also use this because we know that our delta should be smooth across time as well as space. So here, the smoothness term ensures that it's smooth across space, and we would want to add two more neighbor terms to ensure the smoothness across time dimension too. So to show some results, I have synthesized some um, delta and then use like completely random A, B, and theta to put them into an intensity image, which I then try to solve for delta, giving the function what A, B, and theta should be. And this is what I get as a result. Although there are some like differences, I think overall it does show the general trend of how delta should look like. And then with actually captured image of a tuning fork, which basically is the image you see on the right. The left video is the video of its displacement slash delta, and the blue is negative, right is positive, I believe. This is not very smooth, partially because of some phase and sign ambiguities that I am looking to solve after I submit this project. So if you look at it, look at the motion magnified video on the right, it does show some motion across the two bins, that they are kind of moving in opposite of each other. So another motion magnification that I created prior to this project using another method gives this opposite motion that of moving inward and outward of the two ends of the fork, which it's not completely shown in my in this video, but does show a certain aspect of it. So there are spaces for improvement of for this project, and I would like to continue working on those. Thank you for listening.